Welcome everyone. My name's Daniel and I'm the Online Community Manager at the Global CCS Institute. I just want to cover a little bit of housekeeping quickly before we start. Questions are welcome during the webinar, so please submit them whenever you please, just through the question panel that you should have visible on your screen. If we can't get through all the questions at the end of the webinar, then we will still have a conversation with Ernie and pose them to him post the webinar and circulate those responses to you all. The webinar will also be recorded and will be available on our website in the next few days, and I will email you when it is available for download with a link. I would now like to hand over to Kathy Hill, Institute Principal Manager, Carbon Storage.
Okay. Thanks, Daniel. Thanks, Daniel. Thanks, everyone, for joining us today. Welcome. The Global CCS Institute is looking at technical, regulatory, and commercial aspects of CO2 EOR to help understand better its potential roles for CCS. And Dr. Ernie Perkins of Alberta Innovates Technology Futures and our senior advisor with the Global CCS Institute in Storage is joining us today to provide the webinar. Ernie's been involved in acid, gas, and CCS projects for about 20 years as a senior research scientist and has reviewed many CCS projects. His particular specialty is in geochemistry. The talk will take approximately 30 minutes, and written questions to Ernie are most welcome. So at that point, I think I'll hand over to Ernie, and I'm looking forward to hearing his talk.
Thank you. What we have here on the first slide is a sort of a picture, if you like, or a schematic of what a lot of people envision can happen in oil fields. First, we go through a primary production phase, maybe into secondary, into water flood, and then we start to seriously modify the field as preparation to go into CO2-based EOR activities. And in the base of this slide you see in front of you, I've got a picture of actual data from the Weyburn field in Canada. And you can see that after infill drilling, both horizontal and vertical, there was a considerable amount of extra oil being produced as a function of the CO2 EOR activities. The concept is that you'll keep on doing CO2 EOR until such point is no longer economically viable, and in that process a significant amount of CO2 will be stored in the subsurface, and then the site could possibly be converted to a classic CCS site using all the infrastructure, wells and things like that, moving from CO2 EOR to CCS. What the purpose of this presentation is to sort of go through those background issues, some of the points, a high-level view of sort of discussing how do we do it, what are the issues, what do we have to worry about, and maybe we don't have to worry about it, it's just natural process. So I'm going to go through very basically first, once again, a very quick pass. First, what are the sort of properties we need to worry about, both with CO2 and with the oil, reservoir properties, more or less to put CO2 EOR in place. And at the same time in the background, we also sort of know what we have to do for CCS. Show an example of a small field here from Alberta and how effective it has been, and then discuss some of the issues really with the transition from CO2 EOR to CCS, which really is the question. So first, if we're just looking at some of the key properties, the first one we always deal with, especially in CCS, of course, is the CO2 density. Shown on the right is a figure with density as the vertical axis, temperature as the horizontal, with contours and pressure. And basically, for reasons of maximizing our storage potential, we want to be deep enough in the reservoir at an appropriate temperature, so we're above the two-phase region. We're either in a liquid region or a supercritical region. That gives us the most dense form of the fluid. We can pack the most in the reservoir. It has implications, of course, upon relative permeability issues and things like that. But that's what we want. Now, CO2 density for EOR is also important, because if we look at that, we'll find typically our density is going to be less than oil and certainly much less than water. So if we just think ahead to going for EOR applications with CO2, density reasons are going to suggest that we're going to try and sweep a different portion of the water if we just inject CO2. So that's a big positive. But the other thing we must remember, of course, is maintaining a dense CO2 phase does restrict the type of reservoirs, the depth of reservoirs we possibly can use. So there's one of the first positives and one of the first constraints on what you can do. The real reason for looking at CO2 EOR is for miscible flooding. And here, CO2 can actually dissolve into the oil. And this is generally at high pressures or higher pressures. As you drop the pressures, it's only partially miscible down to immiscible. This miscibility is totally a function of the oil you have. The heavier the oil, if we go to an extreme case like the Alberta bitumens, you just can't force in CO2 and miscible under almost any circumstances whatsoever. So immediately from this, we know that we have to have the right oil to be miscible. We also have to have sufficient pressure in the reservoir so we can get to that miscibility region. If we don't, as can be seen on the little sketch down at the bottom of the right-hand side, have a high enough pressure to reach miscibility, recovery drops off quite quickly, quite significantly. If your reservoir is high heterogeneity, well, you probably have to have a higher pressure, certainly on the production side, to make sure that you stay significantly above MMP. You don't want any drops below, because then a number of strange things start to happen. The real positive in all this miscibility, of course, is because of the lower CO2 density and so on, when that becomes miscible with oil, it results in oil swelling. That physically pushes the oil around, makes it more amenable to production. In short, far better production. There's a lot of work going on right now, though, looking at MMP and specifically, and typically you'll hear words like new technologies used for this, for CO2 EOR. Basically, if we can lower the minimum miscibility pressure of the oil in the reservoir, then a lot more reservoirs that are present in the world will be accessible. This could be done, for example, by putting in some solvent like light hydrocarbons or something, or for that matter of fact, using a recycled gas mixed in with your CO2, something like H2S. Now, you may not want to do H2S because of the possibilities that you have problems and issues with your steel on the production side, gas separation and so on. And at this point, given the price and the value of your condensates and so on, you may not want to cycle that back with the CO2 and lose it in the reservoir. However, if there's another methodology that does this, then a lot more reservoirs will be amenable to this technology. One of the other areas of research where there's a lot of potential to go further with CO2 EOR is trying to develop different technologies, different processes, so we can increase the recovery when we're only in partial miscible states. Finally, one of the things that we always have to keep in mind when we're looking at CO2 EOR is asphaltene waxes, mineral scales, things like that, because we are changing our chemical system there significantly, so the possibility of precipitating scale, blocking the formation, lowering permeability, porosity, and so on like that is a very real issue. So all this really implies is we have to do our homework first and make sure our oil and our reservoir is amenable to this process. Let's look at the key CO2 water properties. And the reason for doing this, of course, is probably if we're going to do CO2 EOR, we're going to be injecting water as well. And we'll come back to that in a second. Now, one of the reasons why we'll have water potentially used is CO2 viscosity is much lower than water. And the greater the viscosity range between CO2, for example, and oil, you're going to result in fingering. You're going to have limited breakthrough restricted to small areas. So you need to have a push phase, if you like to call it that has a density closer to the oil. So that's one of the negatives of CO2 is the viscosity range. So once again, we're constrained in what we can look at. The mobility ratio here is also very, very important. And so we got the ratio of oil-water viscosity. If we are at a reasonable ratio, say 2, 1.5 or something like that, there's no question we can push the oil quite well with the water. But if we have a ratio of 5, 6, 7 or some horrible big number, recovery gets pretty difficult. So one of the other new technologies that are being considered for these sort of processes is changing water viscosity with polymers and things like that. Once again, then you put that in your CO2 EOR operation with water alternating gas or something, and possibly you can recover a lot more oil. And of course, the more oil we recover, the more space we have left for CO2. The last thing we have to keep in our mind, however, is that oil is not really a simple phase like water, like CO2. And there's some experimental data just summarizing for one particular oil what the mixing occurs between CO2 and water. And you can see we have a number of 2-phase regions changing, as well as 1 3-phase region there, just about in high CO2 portions. The problem is simply this is pretty complex behavior. We want to avoid flashing back and forth from one to the other, so we want to be in a single phase region. So once again, for most of our recovery processes, this also helps restrict where we're going. So to summarize right now, if we're looking at screening our reservoirs, pressure and temperature are probably the key things we're looking at because they control admissibility. If we haven't got that, the chances of going ahead with CO2 EOR is pretty low. Relative permeability effects is something we also have to look at as well. Some systems are very highly affected and have a very low permeability for CO2. And the fact when you have the CO2 in the oil or CO2 oil-water system, your permeability drops low enough that you're going to have to either be fracking a lot or it just may not be practical. There also has been noted in some systems significant hysteresis effects, and that can impact quite strongly on your production. Whether your formation is oil wet, water wet, mixed wettability also controls quite closely how you do things in the reservoir. All these last 2 points really say is, once again, you've got to go to the lab, take core samples, oil samples, things like that, and really evaluate whether or not your reservoir is appropriate. So, sort of in summary, we can't really go and say, this reservoir is appropriate because I want it to be. It's partially water flooded. There are a lot of restrictions, both on reservoir properties, oil properties, and CO2 that do restrict our reservoir to a degree. There are improvements coming in technology. We're learning how to do things much better. There's no question, but we still have to look at these constraints. Just if we look at the CO2 oil properties on a sketch like this, on the left we have injected pure CO2 stream. On the right we have our pure oil. And what you really get is sort of 3 intermediate phases. Initially, upon contact, you have some of the light components of your oil going into the CO2. We have some CO2 going into your oil, and then we have sort of a single miscible zone. Now this is dynamic. When it first starts to mix, you probably get just a little bit of the light oil components going into the CO2 and a little bit of the oil, and over time your miscible zone phase will increase. This is, of course, if temperature and pressure are appropriate. What this means is, first, these phases change with time, and second, that you have a number of different types of oil phases with different property coexisting simultaneously. It also implies that you will produce your CO2 with your oil. Now, we all see a sketch, something like this, sort of our schematic view for CO2 recovery. We inject CO2 at our well. We have CO2 at one side, a miscible zone in the middle, an oil bank with CO2 and it produces. Well, in actual fact, this is a pretty simplistic sketch. It may be appropriate for a restricted number of cases, but probably we're going to be pushing that CO2 with water, and we'll get into a situation of water alternating gas. A little more realistic snapshot of the reservoir, and this is one that has been shown a number of times now for Weyburn. We have 2 zones, as you can see in the formation of the Mydale, the Marley and the Vuggy, and it's bounded above by an anhydrite zone directly in the Frobisher underneath. And what we're doing is injecting water vertically below a horizontal CO2 injector on the right, and we get a banking of both water, CO2, and then within that a number of horizontal producers and a vertical producer that may have been there for quite a few years, in which we have both oil and CO2 mixed coming through, pure CO2, and ultimately water. And of course, the more confusing heterogeneities are present in the reservoir, the more complex your well structure is going to be in your pattern. The older the field is, the more infill wells, what was there in the past are also going to control that, as well as issues with fractures and so on. So it's just sort of a sketch, a snapshot of something that's a little bit more complicated. So if we're going to go ahead and screen our reservoirs, the first thing is reservoir pressure, MMP. If our average reservoir pressure is too low, we're simply not going to be there. Well pattern, stated depletion. If we don't have enough oil left in there, it's certainly not worth doing. And if we don't have enough wells in place, we might have to drill an awful lot of wells. Or if we have too many infill wells already done, we'll have to look at conversion or doing something else that's different. A key laboratory measurement here is our residual oil saturation. If we can only produce 70% of the oil and our residual saturation is 30%, we're simply not going to get any left, even though we've got a lot there. Wettability, as mentioned before, is critical. Heterogeneities, interwell continuity is also very important, especially in fractured reservoirs. You're really going to have to design your pattern here to take advantage and take care of anything that's causing, like fractures, the interwell issues. Really, it all comes down to the ability to inject and produce fluids at economic rates. And in today's world, the key thing seems to be the cost and the amount of CO2 that's needed. In today's world, CO2 is a costly thing. We do not have credits, if you like, or tax breaks, or whatever mechanism we're going to use to store CO2. So it's one of the most expensive things we can do. So most of the schemes that we're looking at EOR at this time try to minimize the amount of CO2 relative to production, and that's why water is used quite extensively. It's a lot cheaper. If you're actually going to go through and develop your reservoir, you have to start looking at things, for example, like gravity domination versus pattern floods. In gravity domination, we know the CO2 is going to be at the top of the formation, so we can inject pure CO2 there, forcing our system down. We can do both this for miscible and immiscible floods, or do a pattern flood, similar to a water flood in the schematic diagram shown earlier. This more or less has to be decided up front. And one of the issues, of course, is when you're doing a gravity-dominated situation, your use of CO2 is far greater, most likely, than you are in a pattern flood. However, you may have the right geological environment that's appropriate. Wellhead, bottom hole pressures, that also is very important. Once again, MMP is critical. The possibility of something happening in your production system and potentially separating at the base of your production well is a very real thing that we have to look at. Impure gas streams, mentioned it previously, it might help your MMP. It certainly impacts on your surface facilities, your compressor, your field design. So you can't just go ahead and say this stream will work. It has to be engineered in properly. You have to look at the source. And of course, given the cost, you don't really want to go to 99.99% CO2. If you're recycling, your system is going to be impure pretty fast anyways. You have to look up front in terms of how you're going to modify your pattern. Any pre-existing system, we've already gone through and had a lot of production, perhaps 50%, 30%, whatever the numbers are. Infill drilling has gone in to get the missed oil. And now we're starting to put in horizontal wells once again to get better sweep and faster payback. And then you've got the issues that you have to balance your patterns. If you just have one pattern and it's only got class at 5 pattern, a 5-spot pattern, you probably don't have control of pressure within your reservoir. It's going to be going outside that 5-spot pattern, so you have to sort of look at what's happening around it, perhaps upping your pressure in the surrounding areas. You have to do this across the field, or at least in the areas that are around your CO2 flood. You may actually end up on the portion edge of your fields having a whole series of water injectors simply as pressure maintenance and to stop fluids moving beyond your boundaries. One of the things that can happen, of course, is once we flow to your production well and produce, once you start to get CO2 breakthrough or partial breakthrough in the order, and you do get degassing occurring in the wellbore, you've now got a free flow, or if you like, a natural gas lift occurring. So you have to have your production side amenable to that. If you don't have it set up for that, you're going to choke the whole process off. So you've got to consider the status, not just the state of your well, but what sort of pumping equipment you have downhole. Finally, you've got to look at the effects of phasing in. We certainly can't do a whole field simultaneously, not unless it's exceedingly small. So you're going to phase in from one end to the other for the mineral outward, or delay developing certain areas to others, or complete and transferring the CO2 over. And you can see this in virtually every field that's gone through CO2 EOR. And finally, and this is a critical thing, is optimizing your WAG operation. If you are using water, and under today's world with high-cost CO2, you're going to try to be maximizing the amount of water that you're using for a given amount of oil, minimizing your CO2, so slug size becomes critical. Now, it's very clear in the future that when CO2 does have a value, stored CO2 does have a value, then the economics are going to change, and now in our WAG operation we're probably going to be trying to maximizing slug size. Now there are advantages, and many of them, to having large slug size. Our recovery is actually better, but it's often not important enough or large enough to offset the extra cost of the CO2 in today's world. The other thing just to remember is facility costs really go up significantly. Shown here are 3 columns with primary, water flood, and CO2 EOR, and running down the sides are just some of the areas. In primary, basically we have production wells, separation, and maybe some gas separation, and we flare it off or put it in a small pipeline or something, and that's just about it. Water flooding, of course, we need injector wells, we probably need infill drill wells, our oil water separation issues goes up. We now have all the issues with water injection, water treatment. We have to have recycle and make up water, and our recycle costs can be very, very significant. Once we get over to CO2 EOR, our CO2 source and gas compression are huge, but probably we're using more water in the system now. We certainly have more water injectors. Our gas separation costs have increased tremendously simply because we have CO2 breakthrough, and we really want to reuse that source, CO2, compress it, and go back again. It's a lot cheaper using your own CO2 than somebody else's. Everything else pretty much stays the same. So facilities transitioning into CO2 EOR is a very big issue. Here's a picture of JOFFRE, CO2 EOR in central Alberta. It's only a few miles away from, I believe it's a polyethylene plant or polystyrene, I forget which one. And so they're now running in a small pipeline with CO2. You can see one of their wells in the background, nice idyllic fields in the fall. Everything looks wonderful. JOFFRE started off life, as you can see by the field before, originally in water flood, and by the early 70s pretty much had dropped to nothing. There's a little bit of well activity and so on, but essentially the field was watered out, nothing was produced. And in 82, CO2 EOR was ejected. It was initiated, and across the field the daily production ran to 400 to about 600 barrels per day. And it's been running that way ever since roughly January 83. The numbers, if we were to look at them as of a couple of years ago, there's roughly 30% of the storage that's been injected has remained in the reservoir. So we have a good storage site here. Not only have we produced a lot of oil at 450 barrels a day, and even still in 09, we've also stored a lot of CO2. So as a primary storage facility, it's not great, but on the other hand, it is storing CO2 and it is producing oil. So we have the economic write-off there, and we do have a positive effect. And you can see it as of 09, there was about 11.5% of the oil in place recovered, and the goal is up to about 16%. So, and this field is relatively small. It's not particularly big, but it's currently economic and storing CO2. What more can you ask for? If we're going to look at the transition to CCS, and we've gone through and done our CO2 EOR, and we have the thought that we really want to carry it further and become a storage facility, the first thing is planning. And you've really got to start this planning a long time in advance. Traditional EOR in today's world is maximizing oil production, minimizing CO2 usage. If you are transitioning to CCS, your CO2 EOR methodology is going to start to change to maximizing CO2 usage and hopefully still keeping a very high oil production. So you're going to be moving into that in a very different fashion than if you've been doing CO2 EOR over a long period and then all of a sudden decide, now I want to switch to CCS. However, I must emphasize, of course, during CO2 EOR, regardless of whether you're maximizing or minimizing CO2 usage, you still are storing a significant portion of whatever you inject. The other issue is more well, let's say it's more regulations than anything else, rules and regulations. In general, at least in Canada, we have petroleum acts that really are govern how we operate our fields, EOR, any production. There is significant difference in what people think, although regulations are not yet in place. What's the issues for CCS? CCS, we have the issues of long-term liability. EOR, once the wells are properly abandoned, the field's done some property, it automatically goes back to the government in this case. There are possibly very different rules and regulations for well abandonment reclamation. The issue is here now, if you've planned and started abandoning your EOR field with one set of regulations, do you have to transition across to the new one? What do you have to do? These are things that are not yet defined. One of the things that Alberta has passed in legislation, which is quite interesting, is for CCS, there is what they're calling the stewardship fund. Essentially, it's a tax, if you like, on every single cubic meter of CO2 that's being injected. And that will be used for long-term monitoring and any possible remediation that occurs once the liability has turned back to the province. It's not clear how that will apply to EOR activities, even if we stop after that, if we wish to claim CCS. And of course, the final issue here, once again Alberta addressed it a while ago, is does the government even have the right necessarily to allow CCS to occur? Alberta took the position by passing an act in the legislature of actually defining that they owned the pore, they could lease the pore, and they defined the rules and regulation, or the rules, the legal limitations on how this is to occur and what has to be done, and gave themselves the right to do this. Most of the CCS places around the world, however, and possible project sites, are under a special warrant, if you like, of some sort. So these last issues really here are all legislative, they're all rules and regulations. They are a major challenge of bringing things together because EOR is a very different world from CCS, and in part volume is one of the key issues, and liability. But then the naysayers, if you like, is why do I really want to do CCS? If I've been doing CO2 EOR successfully and I'm at the point now that I'm finished my EOR and I want to shut my field down, that CO2 could potentially be very valuable commodity, and we could sell it to the guy down the road. I mean, I've been buying it at what, $50 a cubic meter, $100 a cubic meter, I don't know what. And the guy down the road's got to spend that money. I'm sure he'd jump at the chance to buy that CO2 for $20 or whatever the number that he's happy with doing. So transitioning, it really is going to depend on a value of CO2 stored. Now, until we have a high enough value for stored CO2, this is always going to be a possibility. We can use CO2 in field 1 and sell it to field 2. Just like we use it in field 1, then use it further down in field 1. We don't have to always keep it in the ground. But ultimately, this is not really an issue. What it is, as long as we track it, know where it is, and account for it, every time we use it, we store 20, 30, 40, 50% in the ground. We are not maximizing our storage, but we are getting incremental storage along the line. So really it almost comes down to an accounting issue and going forward from there. One of the key questions is, though, if we want to transition from EOR to CCS, and this is one of the more difficult questions to answer, is when will this occur? Well, if we look at JOFFRE example, it's been running since the mid-80s, early 80s, still ongoing. Weyburn's right now has been running since 2000. It's going to go on for quite a few more years. The Pembina Basin has been, many of those have been running, well, some I guess from late 70s and so on. There's not a clear time when we can draw and say, we're now going to convert EOR, CO2 EOR, to CCS floods. As long as we're making money from the oil, the chances are we will remain as an oil production facility, an EOR facility. There will be incremental CO2 stored, perhaps not as much as we'd like until 1, CO2 is a value, and 2, the oil production is minimized. The thing to remember, though, in these fields is once you get pretty much the whole field covered, and if you started off from one end to the other, they're now producing CO2 they don't necessarily need. We've cleaned off one end of the field, so we're going to be running totally off recycle. So it could be for the last 10 or 15 years of production on a large field that you will not be importing CO2 at all. Just by using, all will happen is you'll be using your recycle and going round and round, and as some of that recycle remains behind, the number of patterns that we're flooding and so on gets smaller and gradually shutting the field down. So it'll flatline if you like. Now that also opens the possibility that we can start to transition the field. So in the early portion of the field that was injected early could now be converted, if you like, to CCS while we're still actively undertaking CO2 EOR on the other end of the field. The real question comes down to is, though, can CO2 injection continue after EOR? And I'm going to throw this statement out that for many of the fields out there we have limited volumes. The reason is pretty simple. We've pressurized up the field during EOR to stay above MMP. The only reason we can do this during a continual injection, of course, is we have continuous production, and that controls the pressure in a reservoir. Once we stop producing, the pressure in the reservoir will rise. If we already are pressurized at or near reservoir max, because we are producing oil, we now have an issue. We can't pressurize it any further, and we have to wait for the pressure in that field to decline or actively produce from around it. So now we have the problem that we have a high pressure, we can't use that field. Now the other ones, of course, you hear about on every time you undertake a risk review. And a risk review for CCS almost always points out there are always potential well issues. That's one of the things. Everybody has this image in their mind of potential pins going through the pin cushion. And finally, in an EOR system, monitoring may be a big issue. Now, I'm going to address these last 2 points a little bit. The other thing that we have to mention is other fields probably won't have many of these issues. If they're offshore or something and they only have 1 or 2 wells, or if I've got a couple Darcy permeability running through them, my pressure isn't going to stay very high for very long, so they probably have a very high potential for CCS activities. So once again, another constraint on how we can go do it and what fields we can do it. Now on the well issue, I'm just going to show some public available data. You can get it from the regulators online in terms of the Weyburn area. In the upper left-hand corner, there's sort of a sketch, a little in sort of a pinky gray background, showing the Weyburn field in brown and the sort of phase rollout they had planned initially back in roughly 2000. And then there's an expansion of phase 1A just off the one side. And there's 2 lines going across that roughly show where it is on this map in that portion of Saskatchewan. Now, unfortunately, the lines going across are not exact, but you'll see the impact of that in the next few slides. I must apologize at this point because you'll see down in sort of the central bottom that each one of these sort of squares that we have in there that has the inside pattern is roughly 1 mile on the base. So we've got 4 smaller units are roughly 1 mile. And of course, most of us are working in kilometer these days. What that means is if we go roughly to the center of this pattern, we've got 1 kilometer, or 1 mile going around it. But if we look at sort of the typical range across the whole thing, we're plus or minus, say, 5 miles sort of over the whole area here. So putting that in perspective. Now, if we look at the historical records, during 50 to 55, 1 well was drilled. You can spot it down in the lower left-hand corner in this area. So total number of wells are 1. If we go up in 64, there's about 511 additional wells, so we got 512 wells. Now you can start to see the development around the Weyburn field itself, and it gives you an idea of the well density. If you look at that, it's clearly being done in a 5-spot pattern, central production at this point being set up for water flooding later. There's on the side a legend. I would just suggest ignoring it. What it is what the status of those wells at the current time. If we go on to 85, you can see there's about another 150 wells drilled, or 140, I should say, 600 wells. We've now gone into water flooding with line water flooding, actually line drive to a large degree. So well density is up. If we go to 1991, now we're really into water flooding, and a lot of infill drilling has occurred in areas that were not being swept properly. So especially if you look down to the sort of central lower right, you can see quite clearly there's a lot more wells in a lot of areas than there were before. You can also look at the upper left-hand corner and start to see more wells. These are outside of what well, which is now snow was previously in Canada's Weyburn Field, people are starting to produce significantly outside the field area itself. If we go up to 2000, and here's where the infill drilling has switched over to horizontal wells. It's looking a lot messier. The long straight lines are horizontal wells, and you may or may not be able to see the details, but many of them there's 2 or 3 wells coming off the same point and diverging and running parallel, sometimes 4, 2 to the northeast, 2 to the southwest. The positioning of these wells is largely being driven by a fracture pattern within the reservoir and maximize recovery during the water flood. And this is also in preparation for the CO2 flood coming along. Finally, here's our well density as of 2011. During the last 11 years, another 780 wells have been drilled. And within this area here, we've got over 2,000 wells. And this is not the complete Weyburn Field and surrounding area. I'd like to point out to you as well, once again, our 1 mile block down, shown down in the lower right-hand corner. If we look at a typical sort of 1 million ton per year storage facility, you sort of have a number in the back of your mind if they run 5-10 years that you'll have maybe a mile sort of CO2 plume around your injector, but you could have as much as say 20 kilometer plume around there in terms of pressure plume, depending what you define your sphere of influence. So we look at this, and the first thing that would happen in any sort of review would say, whoa, we've got a lot of wells we have to validate. We have to know what the integrity of those is because they're within a sphere of influence if I was to go ahead and do CCS at this point. So the key issues that this all brings up then is how to check, maintain, enforce well integrity at a reasonable cost. And there are a lot of wells. The next point is, and I'm just going to, well, I'll leave it the way it is, but up in the upper left-hand corner, the wells were not part of the field. They're continuation of the field, but not on the same ownership. So now you have the issues with potential interference if we just start to go to CCS with neighboring resources with potentially different owners. And finally, the other issue is how to ensure that the neighboring wells field within the sphere of influence, whatever it is, are maintained and abandoned as the same level as will be done in the CO2 EOR field or will be done for CCS. Certainly within the field itself, any responsible operator will abandon them subject to whatever conditions are appropriate, but we can't guarantee that the areas outside have been or not. So that is another major issue that has to be addressed on the conversion. Monitoring is something that we look at in terms of almost all CCS. The vision that people have and the public has is this large plume in the subsurface that potentially can migrate upward and affect potentially groundwater or something else in that case. So I think it's pretty much accepted that we have to monitor. In an EO operation, we've got a problem here. We've got old CO2 from the EOR operations, new CO2, what was there before. We don't always necessarily know that information. Where was the CO2 from in a lot of the cases? Because it is essentially an industrial site, we've got a lot of residual signals around. So this really complicates the monitoring as well. Once again, what are we monitoring? Was it from something else? I mean, tracers are very commonly used in the EOR world, and if I try to put a tracer with my CO2 that I'm injecting, now I have problems with trying to interpret that signal, and contamination pretty much kills me. And of course, we're probably a little bit late now here for baseline measurements, which is we'd like to have that really. How else can we understand what's a real signal versus a false signal? Now, can these issues be dealt with? And the short answer is yes. There's no question they can be dealt with, but you have to plan from up front. The first one, why store rather than reuse? And it's the same one that we come back to all the time. Until there is some value for storing CO2 in the ground, there will be no incentive to store it. So it's absolutely critical here that we get the legislative assemblies moving and establish what are the conditions that storage will occur under, what are the financial controls. And then once again, we have to agree on standard accounting regulations and how we're going to measure it and find out what's appropriate. Neither one are, well, I shouldn't say difficult. Maybe they are difficult, but they're certainly doable, and I think a lot of people are working on them around the world. When will EOR finish and CCS start? Well, it's not really important because CCS does store CO2. The CO2 EOR stores CO2, I should say. And so while we're recovering, we're going to store CO2, 30% or whatever our magic number is for that field. It's going to work, and we are going to produce oil and use it. CCS can start when and where is as necessary. And it may be on the field in 10, 20, 30, 40 years if it's an appropriate field, or it may start in many of the other sites that we have. So really it's just a question that I don't see any reason why the two can't cohabit in the same time, and when it's appropriate, EOR can become CCS. The big one that people will focus on, and it is scary, is the well issue, because in CO2 EOR. And really, are they onerous? And I don't really think so. Because right now, anybody who is producing and using CO2 EOR is already dealing with them under the rules and regulations of the time. So it's already happening. And I think we have to recognize that the industry has the ability to do this. You can go ahead and do it. We have lots of experience. And if something has happened, we've had lots of experience dealing with that under sometimes very, very difficult situations. So I don't see that as an onerous issue. Rather, I see it as one, once again here, of a regulatory issue. The appropriate agencies, in Alberta would be the ERCB, have to find the appropriate rules and regulations under which CCS, or CO2 EOR, is going to go ahead and deal with their wells. And after that, it's just a question of proper technique. Can we monitor without a baseline? Well, I'll take the fifth here first and say more research does need to be done. And then the second half saying many modern fields are already monitoring. If you are running seismic to see if your CO2 is already gone, essentially it's already happening. Into the modern technologies, for some things, if we have a clear enough signal, a baseline may not be necessary, but we have to ensure those signals are real and strong enough to be used. They're robust enough signals. So we do need to have more projects, for example, like the Otway, like the Frio, and things like that, where monitoring technologies are tested, and we do that in real situations. We need some deliberate leakage tests, so where we'll release CO2, and of course one or two of those are happening. We need more of those, so then we can move into these more mature CO2 EOR fields, and when the transition occurs, if it occurs to CCS, we have enough knowledge that we can then go ahead and monitor and limp along, if you like, without a baseline. Is interference with neighboring resources, the sphere of influence, a deal breaker? And once again, I think the answer is very, very clearly no. There's many cases here where we have resource interaction. The famous one in Alberta a few years ago was gas over bitumen, where you produced the natural gas, it made it more difficult to produce the bitumen, and vice versa. And basically that goes back through, in this case, negotiation, or it can be solved directly through regulation. And it's not particularly a big deal, it just takes time and effort, but it can be handled for the existing areas. For CCS in the future, once again, specific regulations when they are developed and the applications are made for the field will take care of that. So once again, I'm pushing this back in the regulatory agencies and saying it just needs clear definition there, and that takes care of that. And then finally, the final question, what this all started with, is can CCS be implemented? And the question is, we can have it after CO2 EOR, depending on the specific field and reservoir properties. And to do this effectively, it's going to take planning early in the CO2 EOR process, and decisions have to be made then whether you're maximizing your storage potential through the EOR process and preparing for that transition. So, thank you very much.
Well, thanks, Ernie. We just have time for just a few questions that have come through. First couple that have come from Ahmed Adwila from Stantec. He sent in a couple of questions, and the first one is, how are we going to offset the cost of transition from CO2 EOR to CCS?
Well, I think that's probably the biggest thing that worldwide we as a community that's interested in CCS have to face. And that's clearly legislative, intergovernmental panels, and so on. We must have some unified way of giving either credits or taxing CO2 or somehow making it economic or at least financially viable to go ahead and do this. So really I'm going to have to push that one back and say that's a legislative issue. People are looking at it. We do have taxes on carbons in various jurisdictions around the world, so it has started. And I think as time goes on, we're going to develop a better understanding of what it costs and raising it up enough so people are actively interested in doing it for the financial reasons.
Okay, so you're saying that'll be a bit of learning by doing and getting some more experience in that area.
That's absolutely critical. We have to have pilots out there capturing so we know what the costs are. We have to have CO2 storage sites, CCS sites, operating so we know what the costs and the issues are there to develop good hard numbers of what this process will cost. And then we have to have the tax or credit to cover that sort of thing.
Okay. Well, Ahmed had a second question, and it's, is this the right time to move from CO2 EOR to CCS, taking into consideration that we really don't have regulations in place? And that's Ahmed's question verbatim.
The answer to that one is like the other one in many ways. And until regulations are in place, it's pretty hard to develop a new process. And as I say, some jurisdictions are putting the regulations in place now and putting down the rules and so on, so people are aware of what they have to do and go ahead and do it. So I think we're getting to the point, certainly CCS is going ahead. There is not the same degree of regulations in place for a transition, though, from CO2 EOR to CCS. And that's something that the regulators really have to address. I don't think you can move forward except unless you have a special writ until the regulators get their act in place. Having said that, most of the fields under which CO2 EOR will be taken are still relatively mature, so I think we have time in hand. We're going to be storing CO2 in them just through the EOR process for considerable time, tens of years and so on. So we might not have that many fields worldwide that we really have to worry about that at this point. So I think the regulators have some time. Okay.
I think we've just got time for one final question. This one's from Dr Ernie, and Dr. is the project director at AMEC, and he's asked, he said, I'm interested in Ernie's comments on any experience of EOR and horizontal wells, and we saw some horizontal wells in your presentation today, Ernie, but particularly for the reuse of existing injection and production wells. And would you care to comment on that, Ernie?
Well, I think first generically, horizontal wells are a great solution to recovering a lot of oil, if you like, up front fairly fast, and as such getting your capital costs back relatively quickly. In most horizontal wells you have high production, especially high production at the start, and you get your payback very, very quickly, and they're very, very important. There's no question in CO2 EOR they have a place. Once again, I'm going to sort of back off a bit. It depends on the reservoir, it depends on how you drive, it depends whether it's fractured or not, all those sort of rules. But there's no question that I think most fields, and certainly a number that I've been involved with, all are drilling horizontal wells. A lot of them are still in the learning stage, however. They're putting in horizontal wells and seeing, are they worth it? So there's been some short horizontals go in, some as short as a couple hundred meters, and of course some up to 1,000 meters and longer, and so on going, as people learn. So I would sort of say first, looking to the future with a crystal ball, yes, horizontal wells are going to be critical. Second, we don't have lots and lots of experience with them yet. That's the sort of thing that's currently happening. If we step ahead and look at CCS, however, horizontal wells, because of potentially the very long zone that we can perforate, let's just say we have 1,000 kilometer of open hole or perforated hole interval, that potentially opens up a lot of reservoirs to CCS that we wouldn't otherwise have. If we have very low permeability, low injectivity, we have the potential then of having 10, 20, 100 vertical wells being replaced by one very large horizontal, one or two. So if the formation is such that it's lower permeability, we may be forced to go to CO2 EOR using horizontal wells. In terms of the reuse of wells in the CO2 EOR wells when we're coming to CCS, we probably want to be a little careful with that. It's going to depend on on the vintage of the well, how it was completed, how it was cemented, all those sort of issues. What is the status of the well? So it has to be gone through and looked at very, very carefully. However, these do offer, and one of the big things is a lot of potential sources for well monitoring in the reservoir for CCS. We've got them in place, and all we can do is perhaps say cement pressure transducers down there, or put in fluid sampling, or put in some downhole cross-well facilities for monitoring with cross-cell seismic or EMI or something else like that. So using of the existing wells is going to be, I think, very important from a monitoring perspective. I do not see them being converted very much to a horizontal well. I don't think it is viable. They're often not big enough, and we don't know the status and so on. So the actual injectors and so on in CCS will be a new well, most likely, unless it's drilled very late with that sort of in mind when it was prepared. But the wells, existing CO2 EOR wells, will be very valuable in the monitoring side.
Okay. Thanks for that, Ernie. I'm afraid we're running short on time now, and we're going to have to wrap up the webinar. But certainly, if listeners or attendees of the webinar have any further questions, please submit them to Daniel on the email address that's provided as part on the webinar panel, and we'll try to get back to you. And I'd like to thank you all now for your attendance. The webinar is going to be recorded, and it'll be available on our website next week. And we'll also, of course, notify you, all the people that have registered, of its when it becomes available. I certainly hope that you found this webinar valuable, and thanks again to Ernie for presenting. And we'll be back soon with another webinar next month. Look forward to hearing any further questions in the interim, and we'll keep you posted on the next webinar as soon as we've got the dates firmed up. Thanks again, and so long for now.
Welcome everyone to this supplementary recording where we're going to cover the outstanding questions that we did not have time to cover during last week's webinar, CO2 EOR and the transition to CCS, setting the stage and issues. Thanks to everyone who submitted questions during the webinar. We had a great response and we really appreciate it. My name's Daniel Loyston, Online Community Manager at the Institute, and with me again I have Dr Ernie Perkins from Alberta Innovates Technologies Futures. Welcome, Ernie.
Thank you.
We'll jump into the first question, which comes from Luke Warren, a Policy Executive at CCSA, and Luke asks, are there any CO2 purity threshold requirements for CO2 streams used for EOR?
That's a very interesting question. There's two reasons to be concerned about this. First, obviously, is on the surface facilities, on the compressors, and of course for corrosion issues on pipelining and so on. So there we want to have a dry system, preferably. It's a lot cheaper, and we want to have as little aggressive material components in there as possible. If you have lots of methane in and so on, then it increases the stability field of the less dense phase, for example. In the subsurface, it's not quite so clear, and it depends on the impurity. If you have a light hydrocarbons or condensates in, it actually may lower the MMP, and so then you'll have a very good effect. Other gases present, like nitrogen and so on, may be very detrimental. So as a first cut, you probably want to put in reasonably high purity CO2, say 95% into the reservoir. That seems to be a number a lot of people are using, or higher for that matter of fact. But then as you recycle, you'll find it'll be less and less pure as time goes on.
Excellent, thank you. The next question comes from Cheryl Wilson from Bloomberg New Energy Finance. She's an analyst there, and she asks, do you think all companies engaged in EOR will really ever want to switch to CCS, i.e. is the liability really worth it for an oil company that's already making money by producing oil?
Well, that's another good question, and that's really one from a regulatory and an administrative side. The companies will not switch to CCS until the revenue that they obtain by producing oil is less than they potentially can get from CCS. So first, in the absence of a carbon value, if you like, for storing it, whether it be incentives or a credit or whatever the case may be, there is no incentive to go to CCS. Once that's there, then each company would have to make their decision about the short-term liability, whether or not that is an issue or not. Certainly if the liability is clearly stated and what their criteria are that the companies have to do, it does make the decision easy to move ahead. But the liability has to be defined by the regulators. So in short, once we have a value for CO2 and the issues of liability are clearly defined, then each of the operators will make their decision and move forward one way or another.
Sebastian Reno, Director M&A and a Senior Reservoir Engineer at PNP Paribas, has asked you, how many CO2 EOR floods use anthropogenic CO2 today and where are they located?
That's something I only know a small amount of. I've actually never looked it down. Certainly the biggest, Weyburn, is using CO2 from the North Dakota coal gasification plant, so that's our biggie. And then next to that, of course, is Apache's field, the Midale field, slightly to the east of that. The small field that I mentioned in the presentation, at JOFFRE, is using it from a polyethylene plant. So that's going ahead there. Most of the Permian Basin CO2 floods in the U.S. are using CO2 from natural reservoirs, and so it's being pipelined down. There are some new deals that have been signed to use CO2, anthropogenic CO2, and these are moving forward, but at this point I think it's very safe to say that the amount of anthropogenic CO2 used in the U.S. EOR fields is quite limited. So I'm not familiar with what's happening elsewhere in the world, so I can't really comment on that.
Okay, thank you. The next question from Subash, who's a Senior Reservoir Engineer at BP America, has sent in the question which asks, how much CO2 as a percentage of HCPV is expected to be stored in Weyburn when the CO2 EOR is finished? How much more CO2 is projected to be stored after the end of EOR, if any?
Well, I'll answer the second half of that first. At this point, Weyburn will keep on injecting CO2 for probably till 2035, 2030, somewhere in there, I think 2035, at which point they're planning to go to a recycle mode. That is, they will still continue to produce CO2 and reservoir gases, recycle and re-inject. This could continue on quite easily for another 15 years and so on. Overall, they're not planning to go ahead and inject at this point CO2 as a CCS option. It's quite a distance in the future, and they'll know better when the time comes. With respect to the first question, I believe it's 30 million tons total is what they're planning to have injected by the end of EOR, and unfortunately I don't know what that is in terms of hydrocarbon pore volume.
Okay, our fifth question has been sent in by Anthony Benham, who's a Business Development Manager at the National Centre for Carbon Capture and Storage, and his question is, isn't there a danger that CO2 EOR will just be seen by the public as a way for the oil industry to continue with business as usual and that it's not actually a viable CO2 storage solution?
I think that's one of the main issues we have in publicizing, if you like, making the public aware of the process that we're undergoing. It's certainly been an issue that has raised, and a lot of people are using it to argue against CO2 EOR and resulting CCS. So what I think we have here is a clear case that public education, public awareness must be raised by those people who are doing it, and educating them that this is a viable storage mechanism. So it's something that we all need to work on and needs to be carried forward.
Thanks, Ernie. Our last question comes from Eric, who's a director at ICON. And Eric's asked, when you say that the JOFFRE field has stored 30%, has the other 70% been released to the atmosphere, or is it just the portion that is continually recycled?
Originally in the field, basically the produced gases and so on were not collected and recycled. At this time, they are being recycled. So initially it was just working as a CO2 EOR field and with no attempt to recycle gases. As the produced gases started getting large enough to make collection viable, the